What's happening, everybody? Mr. McCarson back again with another video. And what we're going to be going on a journey this time into the world of chemistry concerning is properties of matter. So we're going to be learning all about the different types of matter that exist in our universe. We're going to be learning how we move from one state of matter into another. What does it mean to phase change? We're going to be learning about the smallest units that are considered matter. And we're going to learn how matter is organized into things like pure elements, pure compounds, mixtures, and what types of mixtures exist out there. We're also going to discuss properties of matter such as intensive versus extensive properties, and we will look at how to discern between physical changes in matter and chemical changes in matter, also known as chemical reactions. So join me on this journey and let's get ready to go. Thank you all for being here. I hope you enjoy. Okay, so we're going to start this journey by asking a question. What is chemistry? So a lot of times we hear chemistry without periodic table, periodic table, periodic table. And we've lived long enough at your age for my classes where you should know like atoms are part of chemistry, and we have that fancy table with all the symbols and numbers on it. But when we talk about chemistry, the major term that everything's centered around is matter. Okay? And matter is something that has mass and takes up volume in the universe. So we'll define matter here shortly on another slide. But we're going to study matter and the changes that matter undergoes because there is a whole universe of variety there. When we look at things like chemical reactions to physical changes, you'll see on the slide down here some examples of chemistry we experience in our life. Things like combustion, rusting, digestion, photosynthesis, kind of a big deal for life on our planet. Batteries, kind of a big deal for the modern teenager addicted to TikTok. Or for me, when I'm playing PlayStation 5 and the battery runs out when I'm on a level of Astrobot. Fermentation, shouldn't be dealing with that at your age, but something that is in uh, part of human civilization for thousands of years. Washing our hands, very important, especially if you're touching door handles around the school. And then finally, Mr. M's favorite, even though it doesn't quite agree with his A1C level, baking of cookies. But all of these involve atoms and matter and changes to that matter in one way or another. So we're going to take a deep dive into matter and how it's organized and what properties define different types of matter. All right, so question. When I say the word matter, what comes to mind for you? What comes to mind? Most of you are thinking of objects, things that have a physical presence or maybe a liquid presence, like the cold coffee in my Captain America cup. Shout out to Marvel. So we have a pretty good idea of matter when we talk about ideas like the atoms, hydrogen, oxygen, magnesium. We kind of associate matter with real life solid objects, right? So I've got like my Expo markers here. Shout out to Expo. Okay, high quality markers for you. Don't forget to use the pinned comment below to save 10% on your Expo markers. No, I'm just kidding. Expo, if you want to sponsor me, let's go. But we often think of physical objects. We can feel them or see them or touch them or experience them, whether they're liquids or solids. The air around me right now, I'm basking in our glorious atmosphere, 78% nitrogen, 21% oxygen, and the remainder made up of things like argon, carbon dioxide, all the pollution and ash from the local wildfires in California. Shout out to our firefighters and police working out there to help keep people safe in these difficult times. And for people experiencing fire, we're thinking of you. And then we might think of states of matter, because we've probably heard that term at some point in our education, maybe in junior high or maybe in Earth and space or in biology. So we often think of solids, liquids, and gases, but we're going to talk about the other states of matter as well too. So things like quantum superfluids and plasma. Okay, so matter we're going to define on the next slide, but I just wanted you to take a minute to kind of think about what relationship does your academic mind and the mind of your everyday life have with matter, because it's all around us, we're made of it. It's largely unavoidable unless you're in the vacuum of space, and even then it gets a little fuzzy. So we're going to take a moment now to define matter on the next slide. Right, so here we go. Let's define this term matter. Matter is defined as anything that has mass and takes up space, or it has a volume that we can measure in the universe. And remember, generally our units for mass are grams or kilograms, or you can use any form of gram on the metric scale. And then for volume, generally we're talking centimeters cubed or meters cubed for larger amounts. And once again, we can expand that out, kilometers cubed for incredibly large volumes. If we're talking about volumes of like entire planets, we're going to use even things even larger than that. Um, and we could also use volume measurements like milliliters, which might relate more for liquids. Okay. Now, mass is defined, and here's going to get a little. This is where mass gets a little. We're crossing into the world of physics here. With Mr. Coots would be proud of this. Okay. So mass is defined as the quantity of matter which a body contains or is made of, as measured, here's where it gets weird, by its acceleration under a given force or by the force exerted on it by a gravitational field. So in our labs thus far, we've actually taken the mass of some items, and what we've done is we've put them on a digital balance, like we did with our density lab. And what's happening is the Earth's gravitational field is pulling down those objects onto the scale, and we translate that into a measurement of mass, basically how many atoms are in that sample, right? It's how much matter is accumulated in that sample. And when we talk about matter, the simplest form of that are the atoms. Okay. Now, once again, the base unit of measurement in the metric scale is the gram. If we're talking SI units, it's the kilogram. So, like internationally, if you're doing science or engineering around the planet, we generally use a larger unit. So, like if you're shipping crates from one nation to another across the ocean, we usually give the mass in kilograms, right? Because larger quantities. But in our lab and at the center of the metric scale, we have the gram. Okay. Now, volume is the amount of space that a substance or object occupies. Okay. Or that is enclosed within a container. So, like for volumes, like a big thing of my wife, no matter how big a house I'm ever blessed enough to live within, it will not be enough volume to contain all the Halloween and holiday decorations my wife wants to have. So, like, I can buy a 5 bedroom house, and 5 bedrooms of volume will not be enough volume to contain all the matter of the Nightmare Before Christmas decorations my wife wants to put up every Halloween, right? So, but volume is a measurement of the space that something occupies, or the space within a defined boundary or parameter. Like you can measure the volume within a box, or the volume within a flask or a jar or a beaker. So volume is how much space an object or container is occupying. Okay. Now, the base unit for volume measurements is the liter in the metric system. And really, what a liter is mathematically is it's a 10 centimeter by 10 centimeter by 10 centimeter cube of pure water that's at sea level, and at sea level because that affects the pressure on it, the atmospheric pressure. We'll get into atmospheres of pressure, or ATMs, later. And also, it should be at 4 degrees Celsius because that's technically when water is at its most dense point. You can say that a liter is 10 centimeters cubed, right? And within a liter, there's 1,000 milliliters. Okay, and this is also where we derive that 1 centimeter cubed is equal to 1 milliliter. Okay, so when we start breaking down types of matter, we have the first category, which are known as pure substances. And pure substances is any substance that has a fixed chemical composition. Okay, so our keyword here is fixed chemical composition all the way throughout the substance. So the first way we think of that about this pure substances is a pure element. Now, a pure element is a pure substance that cannot be broken down into simpler forms of a substance by physical or chemical means. So we're essentially dealing here with atoms. Like pure elements are things like gold atoms, silver atoms, carbon atoms, silicon atoms, copper atoms, hydrogen atoms. And the thing with these is that using either physical processes or chemical, we cannot reduce an atom down into smaller pieces. Now, do atoms have smaller components? Yes, they're called the subatomic particles. More to come on that in a later video series. We're going to talk all about them the entire rest of this year, so they're kind of a big deal. Um, but in terms of matter, if I take a gold atom and I smash it into the protons, neutrons, and electrons that it's made of, it's no longer going to have properties of gold. So once you get down to atoms, that's the simplest form of matter that contains properties of that matter. Okay, so and like I said, that using going back to things like gold and silver, if you want to disassociate those atoms into their components, the protons, neutrons, and electrons, as soon as you do that, the gold and silver will lose their intensive and extensive physical and chemical properties. Okay. Now, let's contrast that with a pure compound. A pure compound is a substance that is made, in keywords here, two or more different atoms that are chemically bonded in a specific ratio. Now, arguably the most famous compound on planet Earth is water, H2O, and we should know that formula. Why is the formula for water H2O? Because there's two hydrogen atoms for every one oxygen atom, and they're fit together with a special type of chemical bond we're going to learn all about later this year, known as a covalent molecular bond. Okay, it's how their electrons interact. The key word for compounds is two or more different elements. Now, compounds can be broken apart into their elemental constituents, but that does require chemistry. For example, with water, we can take molecules of water in a jar and we can hit them with electricity, with electrical energy, and the electricity can actually cause water to split and form hydrogen gas and oxygen gas, which is pretty cool because you can collect them and light them on fire, right? We might see that later this year with a special type of chemical tool. Okay, now you can't do that to a pure element. So I can't take um, carbon atoms and separate it into any other type of substance other than protons, neutrons, and electrons, and they won't have any of the properties. Now, when you break a compound, when you take water as a compound and you split it into hydrogen and oxygen, the hydrogen and oxygen that form will have their own unique properties that are different from water. So, for example, water by itself is not flammable, but if you split it into hydrogen and oxygen gas using electricity, both of those are combustible, right? They're part of combustion. Hydrogen is a very flammable fuel, and oxygen is one of the required reactants in all combustion reactions. No oxygen, no fire. Okay, which begs the question why there is fire in outer space in certain Star Wars films. Come on, science fiction writers, get better. All right, so once again, just to recap this slide, this is a big one. We have pure substances, which are pure elements, and pure compounds. Pure elements are the atoms. Like that's breaking it all the way down to the smallest particles of matter that retain unique characteristics and properties, right? If you take gold atoms and carbon atoms, they're unique, they're different, they do different things. But if I break gold atoms and carbon atoms into their protons, neutrons, and electrons, they they lose their unique properties, and that is a big takeaway. Compounds, the big takeaway, two or more elements combined in a specific ratio. You're not going to get water molecules or water compounds that are H3O or HO. They're always H2O. That's the ratio that defines the compound water. Compounds can be broken down into their simpler elements using chemical processes. You cannot take water and take a knife and physically cut it in half. It doesn't work that way. But you can apply electrical current to split the chemical bond holding oxygen to hydrogen and water. So chemical processes can split compounds, not physical. On to the next slide. All right, so here's a nice little visual diagram courtesy of ThoughtCo. So very, very kind of them. A good resource online for kind of cool chemistry diagrams and diagrams in science for other subjects. We have chemical elements. So these are pure substances that are represented directly from the atoms on the periodic table. Things like tin, S, chemical symbol Sn, sulfur, chemical symbol S, and diamond, which is really carbon rearranged and organized in a very fancy structure, which would be chemical symbol C. Then we have compounds. So we have things like sugar, and if this is table sugar, it's known as sucrose, which was C12H22O11. We've got water, which is H2O, and then baking soda, which is NaHCO3, known as sodium bicarbonate. And the idea with compounds is there are two or more different atoms that are combined in a very specific chemical ratio. We sometimes, well, we're going to refer to that a lot as the chemical formula, right? Like H2O, the ratio 2 hydrogens to 1 oxygen. Now, these crystals are pure substances, and once again, we're going to define why crystals are unique, and they're a unique property of special types of compounds known as ionic compounds. But for crystals, we have things like salt crystals, sodium chloride, protein crystals, which are amino acids chained together. And then you can have things like copper sulfate crystals, which we'll use in some really cool lab experiments. And we'll get into what we call crystal lattice structure and how crystals have really helped us in understanding and using them to classify and study different substances that are useful to human beings and very interesting. All right, so pure elements are represented on the periodic table of elements. So to be very clear, this is one of the most defining, incredible, if you take all of human thought and experiments and recording of information and collective scientific knowledge and put it together, the way that we assembled this chart, it's really not one person, although we will talk later about the person given credit for the current shape of the periodic table you've seen. It's been modified and it's evolved in a number of forms over the last few hundred years, but this is one of the crowning achievements of collective human thought. It is incredible. There are 92 elements all the way up through number 92 uranium, starting from number 1 hydrogen. These are what we call the naturally occurring elements, and then from 93 up until the final element oganesson, these are synthetic. So these have to be on Earth created through processes like that involve, for example, nuclear reactors or particle accelerators. And they do have uses, and we can study them. Some of them are very short-lived. We're going to get into radioactivity later this year and radioactive decay. So hopefully I'll explain to you and you can understand why they're not necessarily able to survive on Earth in a stable form at all, and why their radioactive forms for some of them last a very short lifetime. Okay, now remember the smallest unit or particle of an element is known as an atom. And when we say the word particle, you're going to hear that a lot this year. A particle is the smallest unit of something. So for example, like, once again, let me get my plug in here for Expo. Shout out to Expo Markers. So if we talk about like what's the smallest particle of Expo markers, it is an Expo marker, right? So like if I've got 4 particles of Expos, I have 4 Expo markers, okay? So the particle is the smallest unit of something that retains its properties. And for elements, those are the atoms, okay? Now, once again, we said we got 118 total atoms, and you'll see periodic tables because some of us old timers haven't changed out to brand new ones. In older periodic tables, especially this last row from like 103 to 118, like that last row is not always complete, or you'll see 3 letters there. That's because we were going through, they're very recently discovered, last 20, 25 years. And so there is a process of debate and discussion about what to name them. It's a big deal if you get your name on an element. Maybe 119 will be mecarcinolonium or mecarsonium. Maybe one day I'll have that level of influence and discovery where I'll be 119. Okay, but there's a process by which we have to name them. And so some people are always like, hey, look at that older periodic table. Why does it have gaps in it? Well, we either didn't discover them in those older periodic tables, or we were debating the names. And so they had 3 letters and not 2 because they were kind of placeholders. Different institutions were deciding who would get the credit and get to determine the symbol of the element on the official table. Okay, so that's a periodic table, and we will spend a lot of time. You will get to know this very, very well. Okay, so this is an important slide, and while I like this diagram, it can kind of be a little misleading. So let's talk about it. So first off, when we talk about pure substances, okay, so pure substances are broken down into atoms, molecules, and compounds. Okay. Now, atoms is pretty straightforward. Atoms are the individual elements on the periodic table. They're tiny units. They have a nucleus and an electron cloud. The nucleus contains protons with a certain combination of neutrons, usually, while the electrons do their thing in the electron cloud. Lots more on that to come. We're going to spend a lot of time talking about the nucleus of atoms, or the nuclei of atoms, and the placement of electrons in the electron cloud and what they do, because it's all about the electrons in this class once we get beyond the first unit or two. Now, molecules versus compounds is where it gets a little bit tricky. And as a teacher, I love the analogy of thinking about them as squares and rectangles. So first off, let's define a molecule, and then I want to highlight where this image can be slightly misleading. A molecule is defined as any 2 atoms chemically bonded together. Okay, so 2 atoms chemically bonded together. They could be the same atom, or they could be 2 different atoms. 2 or more atoms bonded together is a molecule. Now, the picture here, all the molecules are the same atom. So this is 2 pink atoms. This is 3 pink atoms bonded. This is 2 blue. But they could be different colors and they're still molecules, okay? Now, a compound has a more narrow description. In a compound, the definition is compound is 2 or more different, keyword different, atoms that are chemically bonded together, meaning ionic bond, covalent bond, those are the 2 main, or metallic bond, right? So here we have, and they also have a specific ratio. So here we have 2 pink to 1 blue. Here we have 1 blue to 1 green. Now, here's the rub. Here's where I want you to think squares and rectangles. So we have a saying, and it's a big deal. Anything that's a compound, so all compounds are also molecules. Why? Because it's made of 2 or more atoms bonded together. Yes, they're different. That's why it's a compound. But they're also molecules because on a broader level, they're 2 or more atoms chemically bonded together. Okay? So number 1, all compounds are molecules. The flip of that is not every molecule can be classified as a compound. So for example, we breathe O2, oxygen molecules. And oxygen is a diatomic, which means made of 2 atoms, and they're the same thing. So you will breathe your entire life O2, okay? And that O2 you can call a molecule. It is a molecule because those 2 atoms are covalently bonded together. However, you cannot call the oxygen you breathe a compound. Why? Because it's not made of 2 or more different atoms bonded together. Now, I think of that as squares and rectangles. Like, you think about the mathematical definitions for squares and rectangles. If you're a square, you are also a rectangle, right? If you're a square, you are also always classified as a rectangle. So we say all squares are rectangles. They're just special because their sides are equal, okay? Length and width are the same. However, is every rectangle able to be classified as a square? No, right? So it's the same thing here. One more time. All compounds are molecules. but not every molecule can be classified as a compound. And that's on what? That's on period. Well, that's old, McCarson. That's too old for class of 2024. On to the next one. All right, so here's kind of just a little bit more of a wordy description of what I just went over on that previous slide, and actually I kind of like this here. So we've got here pure elements versus a compound. So an element, you're just a dinosaur by itself, and then what's a compound? It's two or more different things put together. So you've got a dinosaur riding a shark with a rocket launcher. I don't know, but the meme spoke to me. I liked it. Now, once again, just getting into some examples. Molecules defined as two or more atoms chemically bonded together. These can be the same, they can be different. Doesn't matter. Here are some molecules that are simple molecules, meaning they're not compounds. So like we have molecular oxygen, molecular nitrogen, N2. This is known as solid sulfur, S8, forms a nice little ring, an octagon, or very infamously and important for our atmosphere, O3, which is known by the name of ozone. Okay, so these are molecules that are examples where they're not also compounds. But remember, anything that's a compound is always a molecule by its definition. Now, compound is two or more different types of atoms chemically bonded together in a specific ratio. Okay, and down here one more time because it's so important to get into your minds. Remember, all compounds are also molecules, but not all molecules are compounds. And let's move on. Okay, so in this slide, and once again, I'm not going to go over too much on this one. Molecules, what are they? Two or more atoms bonded together. Compounds, two or more different elements bonded together. The structure, a molecule is usually a group of atoms bonded. For a compound, you've got matter in a complete shape, so they often form things like table salt makes crystals. Okay, now relationship, not all molecules are compounds, but all compounds are molecules. This is the famous one right here. For visibility, some molecules are not visible to humans, like you can't see oxygen, O2, and nitrogen in the atmosphere. However, on the flip, compounds usually are. So you can see liquid water in a cup or solid water as ice, or sometimes you see water vapor as a cloud, like you see water vapor as clouds, right? Depending on the density of that. Okay. And once again, those aren't perfect statements, but they're interesting to think about. And once again, that's not talking about like molecules that are not visible. We're not talking about molecules that are also compounds. Okay. Example, oxygen you breathe is O2. That's a molecule that is not classified as a compound. But table salt is a compound, NaCl, sodium chloride. That is also a molecule by the definition of both. Okay, so we've talked about pure substance.